Okay, I think we can get started. Hello, everyone. My name is Peter Kang from Earth and Environmental Sciences Department. It is my great pleasure and honor to introduce Professor Charlie Werth from UT Austin. Charlie Werth is professor and Bettie Margaret Chair in Environmental Health Engineering at UT Austin. And his research and teaching focuses on reactive transport of water pollutants in porous media, with applications to remediation, especially groundwater and CO2 sequestration. Dr. Werth received BS in mechanical engineering from Texas A&M and MS and PhD from Stanford University. I think Dr. Werth was at UIUC for 18 years and then moved to UT Austin. Dr. Werth made really noticeable and impactful contribution to many fields, but one area that I would like to mention is he's really the pioneer of using microfluidics for biogeochemical reactions. And many of our group's research is truly inspired by Dr. Werth's previous works. So it is my, again, great pleasure to introduce Dr. Charlie Werth. And today we will be hearing about carbonate mineral reactions during CO2 sequestration and implications for induced seismicity.
All right. Awesome. I guess I don't need this. Turn it off?
Yeah.
Okay. All right. Thanks, Peter. It's really nice to be here. I really have enjoyed my visit. Leanne, thank you so much for having me here as well, and being part of the St. Anthony Falls seminar series. So I've been to Minneapolis before. I've been here in the winter before, but I've never seen the river from this perspective. And I know it's not the real winter yet, but it's 80 degrees in Austin today. So you can see why it's winter for me this today. So we'll keep it a little informal. If you want to interrupt me, just let me know if you have a question, all right? I should mention that the work I present today will be primarily from two students, Samantha Fuchs, who graduated and now works for Geosyntec, and then a current graduate student, David Kyungtae Kim. And so Samantha did the core shearing experiments I'll present, and David has been doing the calcite dissolution work. I'm not a geomechanics person, and so I've collaborated with two really good folks in that area. Nicholas Espinoza is from UT Austin, and then Anga Teresa Akano, sometimes goes by Angie. She's at Northwestern, but she was at Illinois. And I got hooked up with these two through an EFRC center that supported a good portion of this work. There's some DFT work in here, density functional theory calculations, that come from Graham Henkelman's group and his student, Mantha Jagannath. And then I have a number of collaborators over the years that have come about through the EFRC that I mentioned, both at Illinois. Al Veloki I've worked with for probably since I joined Illinois in '97 back then, before I went to UT Austin in 2014. And then the student spent time at NETL working with Dustin Crandall for these high pressure experiments. All right, so you guys, I always sing to the choir for one slide, so you have to bear with me to tell you why I care about this and why we all care about it, and what it is. So geological carbon sequestration, you guys probably already know, we capture carbon dioxide maybe at a stationary power source, or maybe we capture it through gas separation in a well, and then we want to store that CO2, so we inject it into some deep formation. And that might be, for example, for enhanced oil recovery. It could be for enhanced coal bed methane recovery, or it could just be into a deep saline aquifer. And most of the capacity in the US is in these deep saline aquifers. And the rationale is, and this comes from this Intergovernmental Panel on Climate Change, that we need to reduce CO2 emissions to control climate change. And carbon capture and sequestration is a big part of this strategy, okay? So that's our overall motivation for why we care about this topic. Conceptually, the idea is that when you capture CO2, you have to compress it. And when you compress it, you take, let's say, a balloon that's filled with a certain mass of CO2 is this big at the ground surface. When we compress it into the supercritical state, it occupies a volume that's about like that. And when we do that, the density goes up from something about air really, really, really low, and we get up to around 700 kilograms per meter cube, where water is around 1. And so we're still buoyant. It's still a buoyant fluid. Also, unlike water, it has a really low viscosity. And so that would be a big difference for it. When we think about when we inject that CO2, we initially get injected as a supercritical fluid. And so we think about there needs to be some low permeability formation that traps it. And we can call that structural or stratigraphic trapping, like a cap rock above that injection formation. Over time, some of that CO2 becomes trapped in individual pores, and we think of that as residual trapping. And this is a time scale here. Maybe over longer kind of time scales, we get more and more of the CO2 dissolved in the pore water, and so we have solubility trapping. And ultimately, what we'd like that CO2 to be trapped as carbonate minerals. And so it precipitates out maybe as dolomite or calcite or some other mineral. And so when we think about solubility trapping, the CO2 dissolves in the water and we get carbonic acid. And when we think about mineral trapping, that CO2 is converted to carbonate through buffering, combines with calcium, and we get calcium carbonate or some other form. So that's kind of the conceptual model. So in the mid-2000s, the DOE funded 7 regional GCS partnerships to look at geological carbon sequestration. And they wanted to assess site costs and safety. And so regional means that these different sites were located in different regions of the US. And they did that both because there were geological differences, but mainly because they wanted different parts of the US to get money, so all the senators and congressmen were happy. One of the sites, the one that I was affiliated with when we had our EFRC, our Energy Frontiers Research Center from the DOE, was this Midwest Geological Sequestration Consortium, and it was located in the Illinois Basin, and specifically right in Decatur, Illinois. And so this Geological Sequestration Consortium was led by the Illinois State Geological Survey, and they evaluated CO2 injection into this basin. All right, so here's an overview of the Illinois Decatur Basin Project, and this is the Archer Daniels Midland site. And does anyone know what ADM does? What do they like to do? And why, where'd the CO2 come from? Thoughts? No? All right. What do you have in your gasoline that farmers love? Ethanol. All right. And so what ADM does is they take corn and they convert it to ethanol. Does anyone brew beer or wine here? Yeah. When you brew beer, what is off-gassing? Like when you brew beer, you have to have a little bubbler there so that air doesn't get in, but you need to let gas out. And that gas that's produced is CO2. And so you take that corn, first you break it down thermally, high temperature and pressure, so you get simple sugars. Then you ferment biologically those simple sugars and you make alcohol, ethanol. And in the process, you release a lot of CO2. And so they capture that CO2, and it's a really pure stream of CO2. So all they really need to do is dehydrate it. So they dehydrate it, meaning they take the water vapor out of it. Then they compress it and they pipe it and they injected it at that site C. They have a deep well that goes into this formation, right? About 330 meters away, they have a monitoring well. And there they're monitoring for pressure and looking at how the pressure increases based on that CO2 injection about 3 football fields away. And then they also have a geophone well for geophysical kind of monitoring. All right, so when we think about the Illinois Basin, specifically, we're interested in this Mount Simon sandstone formation. And this shows the Mount Simon sandstone, and this is the state of Illinois, and it shows the depth. And the deepest part is about 2,000 feet, or not the deepest, the thickest part is around 2,000 feet thick, right? And then if you go out, maybe this is like 1,500 to 2,000, 500 to 1,000, and then it gets less and less thick. Eventually, if I go over into Missouri, there are outcrops of the Mount Simon formation. It's at an incline, and if you drive over to Missouri, you can find the outcrops and look at the stratigraphic layering of this formation, or the Mount Simon formation. But in Illinois, we're looking at something that's about 7,000 feet deep, okay? So one of the reasons we chose the Mount Simon sandstone is because it has a really nice high permeability. But another reason is because it's directly overlain by this Eau Claire Shale formation. And the Eau Claire Shale is a really tight formation, has a really low permeability. And the thought was with this would act as a seal or a cap rock so that when CO2 is injected into the Mount Simon, it would prevent the CO2 from migrating upward, right? Also at this site, if you go shallower, you have a St. Peter sandstone, but here's another shale and yet another shale. So we have multiple barriers for this upward migration. And potable groundwater isn't way up until way up there when you get to maybe the top 500 feet. All right, so this is about 6,000 to 7,000 feet deep right here. All right, so at the Mount Simon Formation, they use different methods to try to characterize that site. One thing they did was just downhole measurements and looking at resistivity and correlating that to porosity. And in the Mount Simon, the larger the magnitude here, the more porosity. And you can see when we get to the bottom of the Mount Simon, we call this the pre-Mount Simon or the basement, it's fractured rock and the porosity drops to almost nothing. And then we have granite below that. And you can see above around 6,000 feet here, we have a very big drop off in porosity. So we have a really good porosity. One thing that's of really importance and interest is at the Mount Simon, our entire injection interval is just over this little piece, the very bottom of the Mount Simon Formation. And that's about a 55-foot open interval. All right. So over this, I don't know, let's say 600 or 700 feet interval, only about 55 feet of it is where we do injection. All right. And the idea is that when it's injected, buoyancy would cause that CO2 to rise. And maybe it would rise up to the Eau Claire Formation and that would form a seal. All right. And the concern was, especially back in the mid 2000s, well, is it going to rise up to the Eau Claire and is it going to escape from the Eau Claire? Is that a competent formation? All right. So just kind of getting back, if we inject that CO2, is it going to rise up to the Eau Claire? Or are we going to have these different trapping mechanisms that cause it to be sequestered in this formation? And then this just shows the capped wellhead. On the prior page was a drill rig when they were doing the drilling. But this is all it looks like now after you get done with the drilling and then you cap it. All right. So one of the concerns, or one of the main concerns, as I mentioned, was this upward migration. And so 330 meters away from the point of injection, so here's injection, and right there is where we have the monitoring well. They looked at pressure. And they did this right in the interval where CO2 is injected, and then they did it up higher. And so let's look right at these 2 or 3 readings of pressure. If we go over, we see that where we inject, or at the depth interval where we inject, we have a big increase in pressure. And then what happens is every time we turn off and on that CO2 injection system, we get these fluctuations, all right? So it's directly responding, this 330 meters away, to that injection. So there's a direct hydraulic connection there, all right? That's pretty clear. If we go up a little shallower, so let's say, well, even this one is a high increase, but let's go up to this one, and that's about what, 9.5, 875, 7, that's about 250 feet away. And we look at this point, we see that there is a little increase in pressure, but not much. And when we turn on and off the well, there's hardly any perturbations. And if we go even shallower, we see that maybe it's even flatter. And so what that's telling us is that it doesn't look like the CO2 is rising up, at least at that monitoring well. And there's not a direct hydraulic connection between the deeper injection interval and the shallower material, even though it's in the same high permeability formation. And so that was a surprise. The people, or when they first started this study, they thought that the CO2 would be buoyant and rise up, and the Eau Claire would act as a cap rock. So that was really promising. All right. One of the things that lends support or was used to interpret those pressure readings was these outcrops. And so this was done by work at Wright State. And they went over into Missouri. And as I said, you can find the outcrops there, and they mapped them. And basically, they took pictures of them, and then they drew over the pictures or digitized it and tried to come up with these different kind of unit bar kind of sequences and look at the grain size and then correlate that to the permeability and then come up with this permeability variation. And so this representation is directly from the outcrop. They took this and then did geostatistics. So you come up with the length scales of these different types of permeability formations or permeability strata. And then they made a big numerical aquifer. And they did this trying to preserve the same distribution of permeability that they had in those outcrops. All right. So what they're going to do then with this numerical aquifer is do a simulated CO2 injection to see how the CO2 is behaving. A little bit more support for this layering type approach comes from geophysical methods. Oh. I think I did. There we go. Where they did this in well geophysics, and this is just the Mount Simon. And they found with this geophysical methods that also they were seeing layering in the Mount Simon. All right. So what happens when they did the simulation? And it should overlay it. Okay. Oh, with the mouse. Okay. All right. Excellent. So when they did the injection, this is the bottom of the Mount Simon formation. And here's the middle of the Mount Simon. So we're not even up at the top. And what they found was that the CO2 plume spread out laterally. And it comes about from this finer scale laminations or variations in permeability. And that was unexpected, but a really nice finding. Because of what it does, it says that, well, for this 1 million metric tons of CO2 that was injected, really very little of the Mount Simon capacity and none of the cap rock is acting as a barrier to this upward migration. So the safety of storing it looks to be better than was anticipated. So that was a really nice thing. But I got a but in there. All right. But one of the concerns came about through other geophysical monitoring. They had these geophones. Each of these dots represents basically an acoustic receptor laid out on the site. All right. And then they also had the down well geophones. And they did this time-lapse vertical seismic profiling at the site. When they did this, they tried to detect both the CO2 plume and also any seismic activity. And they injected 1 million metric tons. An average power plant produces about 3.5 million metric tons a year. So it's not a small amount, but it's not a large amount. But they couldn't detect the CO2 plume until they had 730,000 metric tons down there. And so it was really insensitive to the CO2. So it wasn't a good method to monitor that. But what they did find was a lot of microseismic activity. And so the numbers represent the sequence that the microseismic activity occurred, and the color represents the magnitude. Okay. And so what you see is here's the injection well. Here's the first microseismic, 2, 3, then 4 jumps up here. 5 jumps somewhere, if I'll ever find it. Up there. 6, 7, 8, 9, 10, 11, 12, back to 13, back to 14. So what you might expect if you're injecting CO2 is that ideally, right, your plume goes out radially from the source of injection. That if you're having seismic activity, you're activating perhaps existing faults or fractures that are in the path of that invading plume, and that those seismic events would expand out radially and maybe be greatest near the wellbore and smallest farther away. But instead, what you see is a very random pattern, and you see magnitudes that don't correlate to position. So it was pretty cool. And what it raised was these concerns that we're going to have seismic events at these different injection wells, right? And so this data became available probably around 2010 or 12. And that was a big thing that motivated our EFRC Center. And so from this, all these events are below what you would feel at the ground surface, right? So you aren't going to feel these, but there have been felt seismic events, not big ones, but there has been felt seismic, meaning you feel them at the ground surface, felt seismic events at CO2 injection wells. And so the DOE was really interested in what is causing this microseismicity. And is it going to get worse, or could it be worse at other sites? So when we thought about the possible reasons for this observed microseismicity, we thought, well, it could be from increased pressure from the injection, and that promotes displacement along existing fractures. And that is moving out radially from the well, not uniformly, but along these preferential flow paths. The other thought was we're actually creating new fractures. And just based on the geomechanics, the geomechanics folks didn't think that was likely. They thought it was likely occurring along existing fractures, just because we weren't overcoming that fracture threshold. And then the last thing was postulated was that along these existing fractures, when we create or inject CO2, it dissolves into the pore water to create carbonic acid. And that acidic brine from the CO2 promotes mineral dissolution and then failure along these existing fractures, which are under strain. And so I know a bit about geochemistry. So I thought, I could work on that. But I don't know anything about geomechanics. And so that's why I went and I found Angel Teresa Acano and Nicholas Espinoza to work on this problem. And I thought we could work on the geochemistry part and they could help interpret and give tools to look at this geomechanics. So the objective of this work that was done by Samantha Fuchs was to determine if these geochemical reactions during CO2 injection could possibly weaken the reservoir rock and contribute to these microseismic events. So originally, we wanted to evaluate the effects of acidic brine on strain release in an artificial fracture. It follows directly along what was happening or what we postulated or conceived was happening at the Mount Simon Formation. And we initially tried to use the Mount Simon sandstone. We both tried fracturing it naturally and then seeing if it could hold strain. And then we tried making an artificial fracture, and we couldn't get it to hold strain under the conditions we were looking at and how we treated the system. So we chose a different sandstone, a Bandera gray. And we chose it because it's well characterized, it's commercially available. And like the Mount Simon, it had illite cements. But unlike the Mount Simon, it also had carbonate cements that were holding the grains together. And that makes it more interesting, but also maybe not exactly like the Mount Simon. So I can't say I completely complemented the two, but this is as close as we could get. All right. Yeah.
What you mean by not poor strain is under realistic stress condition, there was always some kind of slip.
And I'll show you how we did that in just a little bit. Yeah. And so the Bandera gray, if you look at it, it's 57% quartz, 16 dolomite, 10% illite, 12% plagioclase, and then smaller amounts of kaolinite and this chlorite. And so we have quite a bit of dolomite, 16%. And carbonates are a very common kind of cementation agent in reservoirs. So I think this is representative of many reservoirs you might have, but the Mount Simon had pretty minor amounts of that. Okay. Also, you can see it had good permeability and a pretty high porosity there. All right. We also looked at thin sections of the Bandera gray to look at or to confirm this mineralogy and to show that dolomites are cementing it together, are these carbonate minerals. And so this is a bright field, and this is scanning electron microscopy, or SEM. And from the bright field, quartz are these kind of clear angular grains, the large angular grains. And then feldspar are these mottled grains. And they're both silicate minerals. The dolomites are kind of translucent here. They show up in the pore space, but they're hard to see. But when we do SEM, the dolomites have an high iron content. And so then you can start to see them really well. And so you find that the dolomites, they fill up the spaces. They adhere to the boundaries of the grain. And you can see how originally the sediments, the quartz and the feldspars, were deposited. And later a secondary precipitation event happened where these carbonates came in, and then you precipitate out these dolomites in the pore space. And so they're cementing these grains together. Also, when you look at these like black lines there or up there, those are clays that are along the boundaries. And so the clays are also acting in some cases as cementing agents, meaning they're holding the grains together. But it's mainly the dolomites are the primary kind of cements. All right, so if you're a real geologist, or if you're a geomechanics person, you might think, I need to use a realistic fracture. And we tried that and it didn't work. So we're going to make a fake fracture because engineers like to make abstractions from reality. And so what we did was we took two core halves and we thought, well, how can we get this system under compressive stress to hold strain? We thought, well, let's make little asperities, these little raised little rectangles, and they're only going to rise up. They're only elevated from the surface 0.1 millimeter. All right. So they're just elevated a little bit, and we're going to make them on both sides of the core. And then what's going to happen is when we set them on top, one is going to fit inside the groove of the other, so they interlock. And so what this shows then is how we have the two cores, we bring them together. And then this is a CT scan. And this would be one asperity from the top part, and this would be another asperity from the bottom part, and here's an asperity from the top part. And so they alternate, so they're interlocked. And then here are the flow channels, and that's where we get the primary flow of this acidic brine that's moving through our system. All right. So we machined this. We had a lathe, and it made this nice pattern. We interlock these, and the idea, this would be a natural fracture, and you have contact points at a natural fracture, which are determined by how it breaks apart. But we create these contacts artificially by milling this and having these 0.1 millimeter raised beds. And that also allows us to be reproducible. When we were trying to make the natural fracture, we basically have like an anvil and a hammer, and you like ping, and then it breaks in half, and every time it breaks differently, and it holds strain differently every time. And so this allowed us to have reproducibility. So, all right, let me look at that again. All right, so this is the work that we went to NETL. They had a triaxial core holder. And so basically you have your two halves of your core, and they're in this triaxial core holder. There's a flexible diaphragm or sleeve around this, and then you provide compressive stress that presses the two samples together. All right, so it's under high pressure. Then what you do is you take these two end pieces, they come and they fit against it, and then you screw one of them, and it pushes one side relative to the other. And when you do that, when you initially move this plug up, you move this part up, but this part doesn't initially move. And then over time, so it's under strain, and over time then, as the strain is released, this side will slowly move until the whole thing is displaced, okay? So initially you move it, this end piece stays fixed even though you move this side, because those asperities are locked in, and over time those asperities give way, right? The strain is released, and then that moves up, and we measure that strain release, right? So we do this for two conditions. We have a brine, it's 0.5 molar potassium iodide, and it's either at pH 4 or pH 8.3. The pH 8.3, that brine we got by just crushing up some of the Bandera gray, mixing it with water, letting it sit for a few weeks, and then taking the water off the top. And that's how we create our brine at the pH that's almost in equilibrium with those minerals that are in the Bandera gray. And the pH 4, we originally wanted to use the carbonic acid, but even though we could do high pressure with this system, it wasn't made to be high temperature. And so we use nitric acid. And we use that because it's compatible with all the other components of this instrument. This whole thing was loaded into a CT scanner. And so over time, we take CT images, and that's how we measure this strain displacement. So, all right. All right, so this is the main result from that experiment. And then the slides after this will look at how to explain what's happening. And so our hypothesis was that if we injected acidic water, that would react with the minerals, that would loosen the contacts between the grains, and we would get more strain release over time. And what we find is at pH 4, we do in fact get more strain release over time than at pH 8. And so it supported our hypothesis that this would give rise to slip along that fracture. One thing though you notice is that strain release though is pretty gradual. And so because the release is gradual, it's not likely that release of strain would result in a microseismic event. That should be a faster event that would give rise to an acoustic emission. A sliding, slow kind of release would not. And so kind of partial addressing of that objective. What happened? Okay, all right. All right, so we did some imaging to try to figure out what was happening and what was giving rise to this strain release. And the first thing was just this laser profilometry, was looking at the integrity of the asperities after or before and after the experiment. So if we just image what that asperity looks like beforehand, we get this nice square raised 0.1 millimeter platform. If we look after the experiment after 7 days at pH 4, we find that it's looks like a rougher, less defined square than if we do at pH 8.3. We can quantify the surface roughness of these asperities. And if we look at this, here's our initial roughness. And after the experiment at pH 4, it rises up and it's statistically higher or greater than it is for the sample at pH 8.3. So the surface is getting rougher. It's undergoing more deterioration, allowing more strain release at that lower pH. The next thing is, why is the surface getting rougher? What's allowing that? And so we postulated that it's because these carbonates would be dissolving. And so we looked at the system initially. So you have the dolomite that's acting as a cementing agent between these different quartz and feldspar grains. And then we looked at it at 2 different pH values. And just by your eyeball, you can't really see what's going on. Maybe you could say, I chose an image that shows a little less dolomite here than it does here. And so we went through and we looked at maybe like, I don't know, 30 or 40 images from each experiment. And we quantified the porosity and we quantified the area projection of the dolomite. And this comes from the surface of the sample after we do the experiment. And we quantified that and we found 2 things. One, at pH 4, we got an increase in porosity in that system after we ran the pH 4 brine through it for 7 days and we got that strain release. So overall, the porosity was increasing from the initial condition to this pH 4 experiment. We also found that the porosity decreased a little bit on the pH 8.3. So maybe we were close to saturation and we were actually getting some more dolomite precipitating in this system. The last thing we looked at for this pore scale analysis was looking at the amount of dolomite. And what we found was compared to the initial in the pH 3 case, we get a drop in the amount of dolomite. So we have less cementation. And so that supports, all these results support our hypothesis that this low pH brine can indeed dissolve out these carbonate minerals and then allow this release of strain to occur greater than you would at this pH neutral system or circumneutral. All right. One thing we want to do to try to quantify the effects on geomechanics is this fracture or this strain test where you look at fracture toughness, or scratch test where you look at fracture toughness. And I was looking in the labs yesterday when I was over in civil engineering, and the original scratch test machine I was told was developed here. It's a little bit different than this device, but very similar. And the idea is we put our sample right here, and we have this little rod, and there's a point at the end. And the point then, it has a loading on it, and that point then sinks down into your sample, right? It penetrates into your sample. Then what you do is you drag that rod across the surface, or you drag your sample across the rod. And as you drag it, you create a groove in your sample. And so as it moves, it's having to dislodge the individual grains from that sample. And from the loading and the force that you have to apply to move it, you can calculate this fracture toughness parameter. And we find that for the initial sample, we have a higher fracture toughness than we do for the sample at pH 4 after 7 days. And at the initial one is very similar to the one at pH 8.3. And so we're decreasing this fracture toughness because of this dissolution of the dolomite in this system. So that was all pretty satisfying. It kind of followed our hypothesis. One thing we did find, though, was that this strain release was slow. It happened over 7 days. And so this results prompted 2 additional questions. So what are the mechanisms of this carbonate mineral dissolution? And can we amend injection fluid to mitigate that? And so if this carbonate is dissolving and causing slip-along fractures, could we add something to the injected CO2 to try to prevent that? So, and I should say, originally these were 2 separate projects that weren't connected, but then they kind of came together in a presentation, so they looked like they were like just intuitively thought out like 6 years ago. No, they just kind of came together because they converged at some point. So we wanted to look first at what's causing this carbonate mineral dissolution, and then how can we slow it down, all right, to prevent or even slow down this slip release along fractures. And so we built this high pressure viewing cell, and it's basically the steel is maybe about 1 inch thick that goes around here. And then we have sampling ports, we have supercritical gas we can bring in, and we operate this at 1300 psi, 50 degrees C, and we have a 0.4 molar KCl solution. And so what you see here is just that brine. You see a piece of calcite that was cut out and put in there. And then up here is supercritical CO2, and it's also dissolved in the brine. And so what we're going to do is we're going to put these pieces of calcite in here. We're going to measure the calcium that's released into the brine to measure how much is dissolving. And then at the end of the experiment, we're going to take out all the brine, dry this off, and then look at the surface of that calcite wafer. Okay. So when you think about carbonate mineral dissolution, there's three mechanisms that people have proposed. All right. One is that calcium carbonate, calcite, dissolves when it reacts with protons, and they promote that dissolution. The second is that carbonic acid promotes that dissolution. And the third is that water promotes that dissolution. And so when you look at the rate of carbonate mineral dissolution, and this is how people model it, you've got the rate constant times the activity of protons, because they promote the dissolution, plus a rate constant times the activity of carbonic acid, because that promotes the dissolution, plus a rate constant times the activity of water, and that promotes the dissolution. And then as you get too much calcium and bicarbonate in solution, then you start to get precipitation, but we never get to those conditions, so you can ignore that. So what we did was we set up the experiment in three different ways. Two of the experiments are the exact same pH, but in one system, we adjust the pH with an acid, I think it was HCl, and so we get a pH 3.11. In the other experiment, we do it with carbonic acid, CO2, and we get to the same pH. All right. And in the third experiment, we don't have acidic conditions, and we have it dominated by water dissolution. So if you look, if I take the activity of each of these ions, or species, I should say, and I multiply it by published rate constants, in the first experiment, dissolution is dominated, right, by the carbonic acid. In the second experiment, this has the largest magnitude, so it's dominated by the proton. And in the third experiment, it's dominated by water dissolution. All right. So we're trying to look at which one of these controls dissolution and how does some ion that we add to the water inhibit this. All right. So what's our additive? For that, we turn to Kishore Mohanty. He's a collaborator in petroleum engineering. And they use this internal olefin sulfonate quite a bit when they do enhanced oil recovery. And carbonate minerals under supraneutral pH and even down to the pH of 3.11, it's positively charged. And this iOS surfactant is negatively charged. It has two hydrocarbon chains hanging off of it. And so you'd expect then that it's going to absorb electrostatically to this positively charged surface. And the original idea we had in our head, and I'll get more into detail with this, was that this iOS would absorb to the carbonate, and then it would protect it from attack by the carbonic acid, the water, or the proton. That was our original kind of crude hypothesis. All right. So what did we get? All right. So the first thing we did was we just looked at what happens when calcite dissolved. And what you expect to see when calcite dissolved, and this comes from our own laser profilometer image, are these rhombohedral pits that are formed. And these rhombohedral pits, let's see if this works. They have acute edges, meaning if you look at this edge, it's less than 90 degrees on this side. And they have obtuse edges here, where you have an angle that's greater than 90 degrees. And then they have kinks. They have a acute obtuse kink here and here, obtuse kink, and a acute kink right there. And all these are places where the proton, the carbonic acid, or the water can attack it and promote dissolution. And in that process, just under regular conditions, or almost any conditions, we expect to see this rhombohedral pit. So, there we go. So the first thing we looked at then, we have this sample in our reactor, and we're monitoring calcium release. So here's the concentration of calcium. In the experiment where we have carbonic acid, we see we get a rapid increase in calcium, and then it plateaus off. All right, let's just look at the black lines for now. In the experiment where dissolution is dominated by protons, we get the same increase, but this magnitude is 1, and that's 25. So we're getting a lot more dissolution with carbonic acid with protons. And then when we have water, we also get an increase, but it's even smaller. It's 0.3. So very little dissolution of water. And you would expect that we get more dissolution under acidic conditions. And if you think about it chemically, you would expect more under carbonic acid, because here, every time we have a carbonate come off of calcium, it combines with a proton and raises a pH. Here, every time carbonate comes off the calcite and dissolves, we have two protons that the carbonic acid can donate without raising pH, so it has a big buffering effect, okay? So we would expect this to be higher. So that follows our expectations. The more interesting result is what happens when we add IOS. So when we add that surfactant, we see that we get quite a bit of inhibition of the calcium release in the presence of the IOS with carbonic acid, compared to the proton, very little inhibition, or you might argue none. And then when we have H2O, we also have some inhibition, but less, all right? And also a much lower concentration. All right, so what is this anionic surfactant, this IOS doing? Oops. All right, hold on. All right, so the first thing we did, again, I'll go back to the laser profilometer results. I'm presenting them a little bit different way here, was look at what etch pits are forming under the three conditions. And so with protons or water, we get these classic rhombohedral etch pits that are forming. But interestingly, and I'll tell you at the end of the talk, I still can't explain why. When we use carbonic acid, the acute edge is truncated, and we're getting more dissolution along this obtuse edge, right? And I'm not quite sure why. If we look then after or in the presence of IOS, something really interesting happens. Dissolution along the acute edge is truncated. We no longer have that. We have a sharp front here. They're triangles now instead of a rhombus. And we have dissolution only occurring along that acute edge. And so for whatever reason, right, we have this dissolution which has been inhibited for these two. For the carbonic acid, we have much smaller and more of these etch pits, but they're much shallower and much smaller. And so we have just overall the behavior is arrested on all sides of it. All right. We didn't have initially dissolution along the acute edge, and now the obtuse edge, once it starts to etch, then it gets arrested, all right, or slows it down significantly. So there are a couple of different approaches we use to interpret this. One of these came from dislocation theory, and I don't have time to get into this, but the basic assumption is that you need a certain activation energy to start the nucleation pit. And if you go through this theory, you can look at the rate of your etching with and without IOS, and it's a function of the saturation state in the fluid, as well as the properties of the material. And we calculate this interfacial energy barrier for nucleation sites. And when we looked at this interfacial energy barrier for activation, in all cases, it was higher when we had this IOS present. So this is kind of a macroscopic, kind of it's an elegant theory, but the end result is kind of a crude interpretation. It's a grouping of parameters that allow us to say, oh, we have higher interfacial energy for these different solutes to come in and attack the surface. Right? The other approach we used, and this is where we teamed up with Graham Henkelman and his group, is this density functional theory, which is kind of atomistic, kind of quantum chemical calculations. And so what we did was use this to calculate absorption energies of the carbonic acid, the proton, and then the water to different calcite dissolution sites. And so we would calculate the energy of the entire slab of calcite. We calculate the energy of these individual molecules. And then we calculate the absorption energy by looking at the molecule with the calcite here minus the energy of calcite and the energy of the molecule, right? So from that, we get this absorption energy. And we did this with I'm not an expert in DFT, but it's with a salvation type model. And so it assumes, just based on the dielectric constant, that there's some kind of polar media around it, even though you don't discretely account for all the water that's in the system. All right, so these are the main results, and these are binding energies. And if y'all remember from thermo, we always consider things which are negative to be favorable. And so that means the more negative, the more favorable. And so if I look, this would be the flat surface of the calcite. This would be the acute edge, the obtuse edge, and then these are those kinks where the edges come together at the corners, acute, acute, obtuse, obtuse, and acute, obtuse kinks. And you find that the IOS absorbs more strongly at all locations except for the acute edge when we look at the carbonic acid and we look at the proton. The water still doesn't absorb as favorably as the iOS. And so when we look at these results then, and we think about why for the proton system, right? Remember, we originally had a rhombus, and then it went to a triangle when we had the iOS present. And so we still had etching along the acute edge, but not the obtuse edge. And so these results would provide an interpretation why the iOS inhibited dissolution along the obtuse edge, because the absorption energy of the iOS was greater, but not along the acute edge, right? So that's kind of cool that we can relate that to DFT. It may also explain, or at least help to explain, why iOS preferentially inhibits dissolution along the obtuse. Oh, I already said that. But explain why calcite dissolution released in the solution is inhibited. In all cases, we found, well, at least for the carbonic acid, that we had less dissolution with this iOS present because of the strong adsorption. If you remember for the carbonic acid, if I don't have it up here, but we didn't initially have etching or dissolution along the acute edge, but we did the obtuse. And then after we had the iOS, even that was inhibited. And so that makes sense. But why we didn't initially have dissolution along this acute edge, I can't explain. And I said that earlier. All right. So we took a look more closely at where each of these individual species was absorbing. And what you find is that when you look at iOS, you look at the water, right, and you look at the carbonic acid, they all bind to calcium sites. So here you see it binding to the big fat gray one here, right? Here you see the carbonic acid absorbing to the gray one. And then if you look at the water, you also see that absorbing directly to the gray calcium. But when you look at the proton, the hydrogen, it absorbs right there directly to this carbonate site. And so basically what that means is that this iOX directly binds to the same sites as the carbonic acid and the water, but not to the proton. And so this may explain why that iOS preferentially inhibits calcite dissolution by carbonic acid and the water, but only marginally for the proton, right? We didn't see that in the calcium release. So that's kind of cool. And it supports, or at least provides an interpretation for why we have those results. All right. So there's still some unexplained observations. One, I already gave you an interpretation for it, but it didn't directly come out of our DFT. It's more just from general geochemistry. Why does the carbonic acid result in much greater calcite dissolution? And that has to do with this buffering capacity. The pH stays lower as we get dissolution, and just has a lot more capacity to dissolve the calcium carbonate, right? One thing we couldn't interpret is why is dissolution on the acute edge inhibited when with carbonic acid when iOS is not present, just by itself. One thought would be that maybe carbonic acid absorbs so strongly that it doesn't detach from the surface or doesn't provide enough energy for detachment, but I'm just throwing out an idea that's unsupported. And I think that's still something we have to think about and figure out. Another one is, why does dissolution occur at the acute edge with water when iOS is present? And our results would tell us that the absorption energy for iOS here are greater than they are for water at the acute edge. And so we would have expected that to be inhibited, but we saw growth along that. And I don't know. That's something, maybe there's some error, maybe we're not thinking something, but can't explain everything or give an interpretation. Another question which we're just starting to investigate, and I don't have any results yet, but it's I've done a lot of work in microfluidics, so I how to do something with microfluidics in the talk, is that how do the fronts of this carbonic acid and the iOAs, how would they propagate under a reactive transport scenario? And so the student, David Kyung-tae Kim, he's looking at, he just built a system where he has a calcite block, and then he has a PDMS kind of, I don't know, a seal and a glass slide that presses against that. And then he has that all in a manifold. And he's starting to look at injecting then either carbonic acid alone or carbonic acid with iOS, and looking at how these etch pits propagate along the surface of the calcite. One of the things that we were initially concerned with was whether under a microscopic technique, we could see these etch pits. And so this just shows another image of experimental setup, but this shows what the images look like. And so in this system, this is before treatment, after it's been polished and it's exposed to just in batch, he exposes it to water. But you can see how under the microscope, you can see these etch pits. And so the idea is, how do these evolve over time in the presence of carbonic acid and the iOS flowing through the system? So that's something we hope in the next 4 to 6 months. He wants to graduate in the summer. He's getting close to done. That will finish. So conclusions. Microseismicity is common at the Mount Simon site and seems likely at other GSCO2 sites. But you can control the injection rate and the injection interval and that injection pressure. And so I think with kind of iteration and control of that injection, you can minimize the concern that there's going to be felt seismicity. As I mentioned, they don't think fractures were induced. And there's also a good stratigraphic trapping at the site. And it indicates that there's little risk, at least at the Mount Simon, for a release of CO2 during injection. I think also at other sites, there's good support that the release of CO2, especially because of the stratigraphic trapping mechanisms here, there's a very small risk of release. I mentioned that I'm not aware of large seismic events at other sites. There's certainly microseismicity at other sites. And as I said, I think that just needs to be kept in mind and monitored. This acidic brine, it induces geochemical reactions. They do degrade the geomechanical integrity of the reservoir where that brine's flowing. They dissolve these carbonate cements that holds the grain together, and they can release strain. But at least in our study, this strain release is relatively slow, so it seems unlikely that it's contributing to microseismicity at the Mount Simon sandstone. And then last, we find that the carbonic acid under these geochemical conditions is going to dominate carbonate mineral dissolution, and it's going to be resident in these reservoirs, or relevant in all these reservoirs. And if we need to slow this process down, or if we're concerned about reservoir integrity, one of the things we can slow that down is to add an additive like iOS. And we find that it binds strongly to these calcium sites and inhibits this dissolutions by carbonic acid and water, and to a lesser extent, protons. And I think that's all. Thanks very much.
Questions?
Thanks for your talk. It was very interesting. I had a question about kind of the long-term implications for the dissolution results. So it seems like you're not seeing kind of the induced seismicity kind of temporally immediate to like dissolution, but is there a concern that like long-term injection would lead to like long-term weakening that might lead to kind of seismicity, say years and decades from an injection event?
I don't know, here I get into purely conjecture, right? My thought would be, based on our experiments, that over a long time period, you'll continue to see strain release in the reservoir, both because of kind of differential pressures that you introduce through injection, but also because of acidic brines reacting with reservoir material. I would speculate that over very long time periods, it would not induce kind of seismicity, but it would just lead to that slow release of strain. I think also, just depending on the amount that you inject, I would expect that over time near the wellbore, you're going to open up pores, and maybe you'll get some wellbore collapse and have to redevelop it. And that could be an issue. But farther away from the wellbore, I think, as many kind of modeling studies have shown, probably a bigger concern is plugging of the formation, where you get buffering and then you get precipitation of calcium carbonates in the porous media part of the formation, not necessarily along the fractures. So that's kind of what I would expect over time.
Cool. Thank you.
Yeah, so my question was just related to your microseismicity kind of assessment. So what are you guys doing when that's occurring to separate microseismicity that is induced from the CO2 injection as opposed to just general background microseismicity that's occurring naturally?
Before they did the drilling, they did geophone monitoring and looked at microseismicity or monitoring seismicity at the site. I can't remember if they did that for 6 months or a year, but they didn't observe microseismicity. It was only during injection and then post-injection for some time period where they did observe the microseismicity. So they had a background reference for that.
Thank you.
I have one question about the experimental results where you showed the strain release with respect to the time, and you said it was gradual. Do you think that could be an artifact from your experimental setup, having like regularly interlocking?
Yeah,
fractures?
certainly. There's many artifacts besides having a regular interlocking lattice. You know, we don't we also have a pretty uniform applied stress. We have strain, which is being applied in a relatively uniform way. We have a temperature and pressure, which are not the same throughout the reservoir. So possibly that we could have a faster kind of strain release under other conditions. That's certainly possible. One of the things which makes me think it's going to be a slow strain release, or at least slow relative to the time scale of microseismicity, is just the mechanism of dissolution is a gradual process. And that's one of the things, in addition to the results, that make me think it would still be a slow strain release. But I don't know. There could be conditions where it is a very fast release that I haven't anticipated or could think about. Yeah.
Thank you.
Yeah, good question.
Just following up on that, assuming it was the gradual strain release that you observed is representative of sill site, I guess, then is it fair to say is the other mechanism, the pressure buildup, is causing microseismicity?
That's what I would anticipate, that it's more, we have existing faults, and those faults are, you know, being held under a given pressure state, and that as we have this pressure wave propagate through there from the injection of that CO2, that's causing a pressure differential that moves that fault. And that's what I would expect. And I think that's kind of the conclusion that, you know, multiple people within the center kind of came to based on this and other work that was done. Yeah.
Great. Any question from Zoom? None? Okay. Yeah.
Okay, well, very, very informative, excellent work. Yeah. Well, although I'm not in the field, so I cannot ask questions inside of us, these people. Yeah. So I have a couple of naive questions. Yeah. One is about the CO2 being a supercritical fluid. Right? This is a little bit embarrassing for me as a fluid mechanics person. So, so what is a supercritical fluid, and about its physical properties? Yeah. So you mentioned, you know, okay, its viscosity is low and the density is lighter than water, right? Yeah. What are other things like temperature, pressure, surface tension, you know, those kind of things like
usually a supercritical fluid it's not a liquid, it's not a gas, but it's somewhere in between. It has its own state.
Okay.
And so it's like I've got liquid, water, solid, and supercritical, right? And so it's its own state. In terms in CO2, it has a pretty high density, lower than water, but much higher than air. Its viscosity is more like a gas. It makes it very difficult to simulate in the ground when you're looking at two-phase flow because of that viscosity. That gives rise to some numerical challenges. Okay. In terms of other properties, for CO2, it's a great solvent. It's hydrophobic. It tends to dissolve organics really well. And so if you go to a dry cleaner, the typical cleaning approach at a dry cleaner, if you take a shirt in, is they use a chlorinated solvent to dry clean your clothes. It's not that it's cleaned dry, it's cleaned without water. But if you go to a green dry cleaner, they'll use supercritical CO2. And so they'll put it into a high pressure and slightly elevated temperature condition to get CO2 in the supercritical state. And it's basically like a solvent that takes dirt off your clothes. So it's quite hydrophobic. The state where you reach supercritical conditions, I think, is around 1300 bar and around 42 degrees Celsius. And so generally, if you go down below, let's say 600 or 700, let me go back on that. I think, how deep do I have to go? I'm trying to remember. I don't know if it's 2,000 or 3,000 feet. I'm trying to remember. I don't remember exactly the depth. where you generally start to hit supercritical conditions where your temperature goes above 42 and your pressure gets high enough. And so any CO2 that exists at that depth because of the overburden pressure is going to be at supercritical conditions. Yeah. Does that answer your question?
Yes. Very, very informative.
Okay.
Thank you. Yeah. And another question is, among those 7 sites, going across the country, besides the differences in the senators and congressional representative, physically, among those sites at a depth that deep, Gisaka, are there any real differences or?
I haven't studied the other sites. I would guess that there's certainly carbonate rich and carbonate poor systems. I would guess that there's both fractured systems and porous media systems. And I would guess that there were differences in probably permeability of the formation in terms of the injection rate that you could have and the depth interval that was needed to inject, and probably the thickness of the formation as well. But that's just if I had to pick them. That's what I'd be thinking about. But I didn't study the other sites well enough to know what those differences are. That's a good point. Yeah.
Thank you.
Yeah, you bet.
Okay, any last question?
I just wonder how do you expect how long the IUS can be sustained in the reservoir, because we can assume we can assume that can be degraded by biologically or chemically.
There is biological activity at 7,000 feet under those temperature and pressure conditions. And so it's possible that bacteria could degrade it. The bacteria is going to be more limited at that depth. I think that the temperature is going to be on the order of, let's say, 50 to 60 degrees down there. And so you can also have just kind of hydrolysis or nucleophilic kind of substitution reactions at that depth that could drive it at those temperatures. I haven't, and I guess I'm getting a long answer to, I don't know how long it'll last, right? But those are all considerations that could lead to its breakdown. In our reaction system, so maybe just as a benchmark, we ran them at 50 degrees C and 1300 PSI. And I think we ran them for, maybe the longest experiments are on the order of a week or so. And so I think the iOS is still fine over that time period, but we don't have bacteria and we don't exactly reproduce the brine. So that's about the goodest answer I could give you. Yeah.
Thank you.
Okay. Any other question?
I was wondering, because this is not something I'm familiar with, is this a long-term solution for carbon sequestration?
Yeah.
And what about methane as opposed to CO2? Can we use similar methods for methane?
Yeah, it's anticipated to be a long-term solution. If you look at the trapping mechanisms, I think they're at least over many thousands of years, it should be permanent. I don't think there's very, very little risk of releasing it over that time frame. Over geologic time, it'll be released, right? As you have changes in mountains and valleys and upheaval and things like that over many, many, many tens of millions of years. Certainly, it'll be released. So it's temporary from that perspective, but certainly in a time scale of many thousands of years, it's permanent. What was the second part of your question?
Could we use similar techniques for methane?
Yeah. So that's a good question. Methane has value. You can burn it and get energy from it. So people are not going to compress methane and inject it. It also presents a higher risk. The handling is more dangerous just because it's explosive. And so for those two reasons, it seems very, very unlikely that we'd ever inject methane into the ground. But CO2, especially dirty CO2, has very little value. We use it in carbonation, right, for some things, but the quantity that we need to sequester is so much greater than what we use that it's basically a waste product. Yeah.
Maybe then we can conclude the seminar here.
Thanks, y'all, for great questions. Appreciate it.
Thank you again, Charlie.
Yeah.